Hi, in this video, we're going to take a look at probability distributions that we use in mathematics and statistics. All right, so probability distributions are used in mathematics and statistics to model and analyze the behavior of random variables. Random variables are those whose values are determined by chance or randomness, and they can represent a wide variety of phenomena, such as the outcome of a coin toss, the number of cars passing through a particular intersection in an hour, or the time it takes for a computer program to execute. Probability distributions give us a mathematical framework for understanding and predicting the behavior of random variables. They allow us to calculate the probabilities of different outcomes, estimate the mean and variance of the variable, and make inference about the underlying population based on observed data. So probability distributions give us a theoretical framework to better understand the data that we're working with. Probability distributions are particularly useful in data analysis and modeling, and they allow us to quantify and characterize the uncertainty inherent in many real-world phenomena. By understanding the probability distribution of a random variable, we can make more informed decisions, develop more accurate models, and make better predictions about future outcomes. Different probability distributions are used for different types of data problems. For example, the normal distribution is often used to model continuous data that's symmetric about a mean, while the Poisson distribution is used to model count data that has a small probability of occurring. The choice of distribution depends on the nature of the data and the population at hand and the problem at hand. There are many, many, many probability distributions in mathematics and statistics, each with their own characteristics and applications. And we're going to go over just a few of these. All right, next thing I want to talk about is expected value. All right, so expected value is the population's central tendency. It's one way of measuring central tendency, but in another video we talked about central tendency, but we were talking about the sample central tendency. So the sample central tendency just says in one number, where is my data along the number line? Well, the expected value says for the entire population of potential values I could see, but I haven't seen, but I potentially could see, where is the central aspect of the population? All right, so, and this is used primarily because it has a lot of very nice theoretical aspects. The expected value or mean of a probability distribution is a measure of its central tendency or average value. It represents the long-term average value of a random variable over many independent trials and is computed by taking a weighted sum of all possible values of the random variable, with each weight corresponding to the probability of the observation. All right, so formally, this is our formula for a discrete probability distribution's expected value. All right, so here we take the value of interest times its probability, and then we add them all up, and that's the way that we get a discrete expected value. Now, when I go to continuous, there are infinitely many numbers, and I can't add them up. All right, so what we're going to do instead, we're going to do a little bit of calculus. I'm going to use the density function instead of the probability. I'm going to multiply by the value of interest. And then I'm going to run some calculus. I'm going to do some integration with respect to the variable. And that will give me my expected value. Now, if you don't understand calculus, that's fine. Don't worry about it. Just, accept that the expected value is the average of the population, and the variance is our way of measuring the dispersion, which we'll talk about the variance next. Intuitively, the expected value represents the average value of a random variable that we would expect to observe over many, many, many independent trials. For example, if we flip a fair coin many times, we expect to observe an average of 0.5 heads per flip, since the probability of heads is 0.5 when I have a fair coin. Similarly, if we roll a fair six-sided die many times, we expect to observe the average of 3.5 on each roll, since each face value has equal probability of being rolled. All right. The expected value is an important concept in probability theory and statistics, and provides a way to summarize the behavior of the entire probability distribution with one number and make predictions about the outcomes of random experiments. It is often used in conjunction with other measures of variability, such as variance and standard deviation, to characterize the shape and spread of a probability distribution. All right, so the expected value is a one-number summary of the population's central tendency. The variance is a one-number summary of the dispersion of the entire population of data, or the population that we could potentially observe. So the variance of a probability distribution is a measure of the spread or variability of the distribution. It represents the average square deviation of the random variable from its expected value, and is computed by taking a weighted sum of the square deviations of all possible values of the random variable, with each deviation weighted by its corresponding probability. Okay, there's a lot of words in that. So if I have a discrete random variable, what I'm going to do, I'm going to take the value of interest, I'm going to subtract off the expected value, the central tendency, and then I'm going to square it, because by squaring it, we make it positive. Then I'm going to multiply that by the probability of observing this particular value. Then I'm going to add all of them up, and that is the variance of a discrete random variable. Now, if it's continuous, I can't add up all the numbers, because all of these little x's, there are infinitely many of them, and it's not possible to add them all up. All right, so what we're going to do, we're going to invoke calculus. All right, so here I'm going to do x minus expected value once again, square it once again. Now, instead of multiplying by a probability, I'm going to multiply by the probability density function. And then I'm going to use some calculus integration, and that will give me the variance of the population. Boom, we got this. Intuitively, the variance represents the average squared distance of a random variable from its expected value, and provides a measure of the dispersion or spread of the distribution around its central tendency. A low variance indicates that the values of the random variable tend to cluster closely around the expected value, while a higher variance indicates that the values are more spread out. Variance is an important concept in probability theory and statistics, and provides a way to quantify the variability or spread of a probability distribution and make predictions about the outcomes of random experiments. It's often used in conjunction with other measures of central tendency, such as expected value and median, to fully characterize the behavior of a probability distribution. All right, so far we've talked about expected value, central tendency of a probability distribution, and variance, which we use to measure the dispersion of a probability population. Now I want to talk about some tools that R gives us to get at particular probability distribution. R has four major functions: density, distribution, quantile, random generator. Density is the formula that we use when we want to calculate the likelihood of a particular value between certain range. So density gives us our probabilities. The distribution function is the cumulative distribution function. That's the probability of a particular value or less. And the reason why we like that is that this will be, like a one-to-one function. It'll have a lot of nice properties. Quantile is, I know the probability that I have. Where do I go to find the x value that corresponds? So the distribution function, I give it an x, it gives me a probability. Quantile, I give it a probability, it goes in reverse and gives me the x value. Now the last one is the random number generator. Now in R has a very nice convention that for density functions, they always start with D. Probability distribution functions start with P. Quantile functions start with Q. and random number generators start with R. And so if I'm looking for, if I know the function for, let's say, normal distribution, that's norm. D norm gives me the density. P norm gives me the probability distribution function. Q norm gives me the quantile function. And R norm gives me the random number generator. And so by knowing like the root word for the distribution, I change the first 4 letters depending on what I want out. All right, now so let's talk about particular random variables. All right, so I'm going to go through a whole bunch of probability distributions. I'm not going to dig into these too much. In the notes on the screen, you'll see that I've got more information in here that you can dig into. I've got each time I'm going to have the density function. I'm going to have the expected value if it exists. I'll have the variance if it exists. I'll talk about when you should use it. Talk about an example of using it in words. And then I'll give you an example using R code for those 4 functions. I'm going to do this over and over and over for different probability distributions. The most important part of this video, if you walk away with nothing else, walk away with this one piece of information: when to use each distribution. Why is this the most important? Well, if you know when to use each distribution, then when real life comes up and something happens and you go like, oh, I need to do something in data analysis, you'll immediately know which distribution you go back to. So the part that I put in the parentheses next to the distribution name is the part that you want to remember for sure. If you remember the name of the distribution and when to use it, you can always go and look up the information, but you have to remember the situation and the name of the distribution. If you remember those 2 things together, then when the situation arises in real life, you can easily look up what you need to know. All right, so Bernoulli. The Bernoulli distribution is used when I have 2 possible outcomes and 1 occurrence. So male, female for 1 person. Yes, no for 1 event. On, off, 1 time. That's the Bernoulli distribution. The next one I want to look at is the binomial distribution. Now this is related, 2 possible outcomes, but it's going to be for multiple times. All right, so let's say there's 5 people and I wanted to model the distribution of gender. Well, I've got 2 possible outcomes, male and female, but there's 5 occurrences. So this binomial distribution will give me the probability distribution of having 3 males, 2 females, or possibly 3 females, 2 males, all females, all males, any combination you can possibly think of. So the multiple times in this case is the number of people that we have. The 2 possible outcomes is gender. So anytime I have 2 possible outcomes and this happens repeatedly, then I'm going to be in binomial distribution. Binomial distribution, I know the number of events. I don't know the number of times of like yes or no, or male, female, true, false, etc. Something is important that we have a fixed number of independent trials with 2 possible outcomes, and the probability of success is constant across all trials. That's an important one for the binomial distribution. Next one is Poisson distribution. All right, so this is the number of counts per time. All right, so here we're going to use this when we're counting the number of events that occur in a fixed period of time or space, and the events have to occur independently of each other and with a constant rate of occurrence. All right, so for this situation, I might be interested in the number of collisions at an intersection per day or per week, something like that. Now, something that is important is that we have to have a constant rate of collision overall over the sample space or sample time, and we have to have independence of each other. So if I don't have that, then I'm in a more complicated situation. But if I see counts per time, I need a knee-jerk reflex of go, hey, consider the Poisson distribution. Next one is the normal distribution. We will use this heavily whenever I'm dealing with averages of numbers or composites of numbers. All right, so if I have averages or like a combination of variables are coming in together to result in the variable I'm actually interested, Typically, that's going to be the normal distribution. So this is going to be used when we have a continuous random variable and symmetric around its mean, its expected value. And we can usually this is going to be that bell-shaped curve that we talk about in so many fields that use statistics. The next one of interest is the exponential distribution. Now, this one is going to be the time between events. So this could be like the time between customers for a call center. This could be the time between how long does it take for a customer to get their meal at a drive-through for a fast food restaurant. And so we're modeling the time between events that occur randomly and independent of each other with a constant rate of occurrence. So here, it could be the time between consecutive earthquakes or the time between breakdowns of a machine. So here, when I say breakdowns, it's not the number of breakdowns, it's the time between breakdowns. So if I see, I want the time, like a stopwatch time, if the variable I'm observing is like a stopwatch time, like minutes, seconds, hours, days, something like that, I want to consider using the exponential distribution. Now, the next one is the gamma distribution. And so here, this is a little bit more complicated, more flexible distribution than the exponential distribution. It's related to it. Here, typically, for this class, for what we're doing in this video, we're going to be looking to this if I have the sum of stopwatch times. And then we'll use the gamma distribution. Now, the beta distribution, we will typically use this when I want to model a variable that is between 0 and 1. And I want something a little more complicated than the uniform distribution, which we'll talk about in a moment. The beta distribution, we can put an emphasis on a particular value, or we could put emphasis on extremes on it. But the values are going to be between 0 and 1 every single time. So for modeling things between 0 and 1, frequently statisticians use this to model probabilities, especially in Bayesian statistics. Now, the uniform distribution, we want to use this one when we feel like things are equally likely to occur. And there's two versions of the uniform. There's discrete and there's continuous. I'm presenting continuous. But if we feel like things are equally likely, it's like each subinterval of equal length is equally likely to occur, then I'm probably in the uniform distribution. And so here, all values within a given range have equal probability of occurring. So the width of an interval is proportional to the probability of occurring is a little bit better way to word this. So if things are equally likely to occur, then I'm probably using I probably want to use the uniform distribution in my modeling. Now, the Cauchy distribution, this one, I'm going to use this when we have very, very, very dispersed data. If I have a situation where things are very, very dispersed, the Cauchy distribution might be the one I want to use. It's so dispersed that that calculus of the expected value doesn't make sense. And the variance, the calculus, doesn't make sense of the variance because it's so dispersed. So we just say it's undefined. And so here, you'll hear statisticians say for Cauchy distribution, heavy tails or high likelihood of outliers. So here, if we think that very, very, very extreme values are likely to occur, the Cauchy distribution would be a good choice to work with. Now, the chi-square distribution, and there is a connection, but there is a difference with the chi-square test. Most people are more familiar with the chi-square test and the chi-square distribution. We're talking about the distribution here. We use this to analyze variance of normal random variables. All right, so for us, if I see variance and I need to analyze it, I'm probably going to use the chi-square distribution. Now, it's important that if I'm analyzing variance, it needs to be from a normal distribution sample, but we'll get into that later when we start digging into hypothesis testing. Now, students' t-distribution, what we're going to do is, remember that I talked about averages and the normal distribution? There's kind of a little touchiness here that we need to talk about. All right, so it works out that what I talked about averages, for that analysis with normal distribution, we need to know what the variance is. So if we don't, what we're going to do, we're going to estimate the variance using, the measure of dispersion that we talked about in another video. We're going to use a sample variance. Now, what I've done is I've invoked like something from my data to estimate the population. And so that invokes additional variability in the system. Because of that additional variability in the system, so when I don't know the variance and I want to analyze averages, I invoke more variance by proceeding by using the sample variance as if it's the true population variance. Okay, well, that changes the distribution. It changes the normal distribution into the student's t-distribution. Student was a pseudonym of someone who was supposed to be doing work, but instead they were doing math. And this was at Guinness, by the way. And so we will use this heavily when we're running hypothesis testing about means. Now, the F distribution, we will use this when we compare the two variances. So the idea on this one is that if I want to compare two variances, I'm going to take the ratio of the sample variances. Now, a ratio, if two things are equal, then the ratio will be close to 1, right? All right, so what we're going to do, I take two variances, I take a ratio. If that number is close to 1, I conclude that they're the same. If it's substantially different than 1, I reach a different conclusion. We use the F distribution to set up cutoffs for us in our hypothesis testing. Now, when what I described about the variances, the sample variances need to be from two normal distributions. Next one, log normal distribution. We use this for highly skew right distribution. So I have a long tail pointed to the right. A long tail pointed to the right. Frequently, we'll see this tail pointing to the right when we're dealing with financial data. And so if I see financial data, immediately knee-jerk response, you need to think probably log normal distribution. Now, the Weibull distribution, I love this distribution. I think this one's fun to work with. This one is used for weakest link time until failure. All right, think about your car. If you get a flat tire, effectively for the purpose of driving, your entire car is broken, okay? Think about your alternator. If your alternator goes, even though you've got good tires, good cylinders, your entire car is broken for the purpose of driving. If your transmission goes, even though everything else is good, the entire car is broken. Steering wheel. If the steering wheel full-blown pops off and no longer works, the whole car is broken, even though everything else is good. The ignition, if you can't get it to turn over, the whole car is broken. All right, so weakest link time until failure, we use the Weibull distribution to model the situation where if one thing goes, the whole thing goes. And that's why I call it weakest link time until failure. Now, the next one is the hypergeometric distribution. In this situation, I have a mixture of items in a bucket, a drawer, in some place. I reach in without looking, grab items out. That's hypergeometric distribution. I got tired of typing, so I didn't put too much about this one. So I feel like I've emotionally reached the end of this video. All right, so we discussed various probability distributions, including the uniform, Cauchy, chi-squared, student's t, F, log normal, Weibull, and hypergeometric distributions. We explained how each distribution can be characterized by its probability density or mass function. That's the D in the R functions, and how these functions can be used to compute probabilities, generate random samples, and perform statistical analyses. We also explained the concepts of expected values and variance for probability distributions, which provide measures of central tendency and spread respectively. We presented the expected values and variance of each of the distributions we discussed and explained how they can be used to make predictions and analyze data. Finally, we explained the basic concepts of density functions, distribution functions, quantile functions, and random functions, the big four in R, which are used to work with probability distributions in practice. These functions can be used to compute properties and of probability distributions, generate random samples from distributions, and perform statistical analyses using simulated data. All right, so here are the homework questions. All right, so that's all I've got for you. Life is short, do math.